Hello, and welcome back to the Mathematical Foundations for Computational Neuroscience. This is the second linear algebra lecture. We're going to pick up pretty much where we left off. So in the last lecture, we talked about a basis. All right? Now we're going to talk about a very important kind of basis, and that being the orthonormal basis. Okay, what does this word mean? It has two parts, ortho and normal. Ortho comes from some root, meaning square or right angles. Normal means length 1. So an orthonormal basis is one where the basis vectors are all at right angles to each other, and their lengths are all 1. All right? Now, why is this a useful concept? Well, if we think of the basis vectors as features, let's say we had a non-orthonormal basis. I'm just abbreviating orthonormal to ON. So for arrows on the plane, here's a non-orthonormal basis. Here's E1, E2. Remember, we talked about interpreting the basis vectors as features in your data set. One thing that you'll notice is that this basis vector, points off in a different direction than E2, but it still kind of goes horizontally a little bit, as well as vertically. So that means that there's a little bit of this feature present in this feature. And that may not be useful because it introduces a redundancy in your description. Because let's say I have a vector that has, something like this. This is my C vector. Well, I'd have to write it as a combination of E2 and E1. Okay? But I'm getting a little bit of the horizontal component from both E2 and E1, so there's a bit of redundancy in my description. What would be nice is if I had a set of features where there was no redundancy. And that is what an orthonormal basis, an orthonormal basis provides. So here, I've got a right angle here, and my vector here is C, and I can write this data vector in terms of the horizontal feature independently of the vertical feature. So that's the idea. It allows you to separate features so that there's no redundancy. Okay, so the concept of an orthonormal basis depends on two things, length and angles. Now, we've talked about how vectors have a length, and we can see that vectors have angles between them, because if I draw two vectors here, there's obviously an angle between them here. But we haven't talked about how to measure these quantities. The way that these quantities are measured in linear algebra is through the dot product. You'll also hear this be called the scalar product. Okay, what does this mean? So the dot product or scalar product is an operation that takes two vectors, and it's denoted with this dot, and it produces a number. Okay? How is that number related to the lengths and angles? Well, if I have V and W, I denote the angle between them as theta, and I'll introduce some notation here. Length of V is going to be denoted as these two bars with V in the middle, and then W similarly. Then the dot product of V and W is going to be given by the length of V times the length of W, a lot of bars in there, times the cosine of the angle between them. Okay? Okay, now that we have a definition of the dot product, how does it relate to an orthonormal basis? Well, remember, if I have two vectors at a right angle to each other, this angle is going to be 90 degrees, or pi over 2 radians. And I'm going to call this E1, E2. Then E1 dot E2 is going to be the magnitude of E1, magnitude of E2, times cosine of pi over 2. And you'll remember from trigonometry that cosine of pi over 2 is 0. So that means E1 dot E2 equals 0. And this is an important feature of the dot product. If the dot product of two vectors is 0, then the vectors are orthogonal. An intuitive way to see this is that they're 0 because there's no projection of E2 onto E1 and vice versa. See, the E2 goes in none of the same direction that E1 goes. So the dot product kind of measures how much the two vectors sort of overlap, and here there's no overlap, so the dot product is 0. And note that the dot product is 0 no matter what the lengths of E1 and E2 are. Okay? Let's talk about what happens when we dot product a vector when itself. From our definition, this becomes E1, the magnitude of E1 times the magnitude of E1 times the cosine of theta. But these are the same vector. So if we draw the picture, it looks like they're laying on top of each other. Sorry. And so the angle equals 0. And cosine of 0 is 1. So this becomes just the magnitude of E1 squared. All right? So that gives us a formula for the length of a vector. The length of a vector, E1, is going to be the square root of E1 dot E1. And this quantity has a name, and it's called the norm. All right. Now, let's say, okay, we've kind of, it may seem a little bit confusing at this point because our definition of the dot product involved the length and angles of between vectors, and we kind of use the dot product to figure out what the length and angles of the vector should be. We don't have any formula to compute the dot product itself. If I were to just give you some vectors and say compute the dot product, you'd have a hard time doing it. So let's see one way to do it, and this is where the utility of the orthonormal basis comes in handy. So if I have two vectors, and I write them in components with respect to an orthonormal basis, and we're working in an n-dimensional vector space. So these are our basis vectors. They are orthonormal, and these are the numbers that represent the vector that are called components. And we have W here, and we have W1, E1. We're writing these vectors in the same, with respect to the same basis. So we use the same basis vectors, plus Wn, En. And I want to compute V dot W. Well, here we go back to the axioms of linear algebra, and we have the distributive property and all the scalar multiplication and addition properties and associativity. All those properties lead us to the formula where we end up with the formula for this by doing these together is V1 times W1 times the quantity E1 dot E1 plus V1 times W2 times the quantity E1 dot E2, and this goes on for a long time, and then we'll have W1 V2 E2 dot E1 plus v2 w2 e2 dot e2. And we have a big long amount of sums, but because the fact that the basis vectors are orthonormal allows us to simplify this. The first property, the orthogonality property, means that all of these dot products where the basis vectors are not the same, this equals 0. This here is 0. Why? Because the basis vectors are orthogonal with each other. The second property, the normality property, means that the dot products of the basis vectors with themselves, which is, remember, the magnitude of the vector squared, is going to be 1 squared, which is 1, because the vectors are normal. They have length 1. So that means this sum simplifies. All these cross terms cancel out, and all of these diagonal terms stay in with a factor of 1, and we get the formula for the dot product when you're working in an orthonormal basis as v1 w1 plus v2 w2 plus all the way up to plus vn wn. Okay, this is a simple formula, and this is one of the reasons that working in an orthonormal basis is desirable, because if I weren't in an orthonormal basis, then what would happen is I'd have to keep track of what the magnitudes of all the basis vectors were and the dot products between them in order to compute the dot product. Now, it's important to note that the value of the dot product is independent of the basis. This is an important point. This dot product doesn't depend on my choice of basis vectors for the vectors. They just have to be in the same basis, which is why we can work in an orthonormal basis and get the value using this simple formula and use it in whatever application. This is also important too because we talked earlier, when we change bases, we're basically changing the set of features that we're using to describe our data set. And we want the quantities that we measure, like how similar a piece of data is to another piece of data, to be independent of how we describe the data set. So that's an important point. In the problem sets, you're going to work through a procedure, an algorithm, called the Gram-Schmidt process, which allows you to take a basis and from it construct an orthonormal basis. And you'll see how that works in the problem set. Let's do some examples with the dot product that we've just described a formula for to get a feel for how it works. So when I write vectors and components, I've been doing it this way, or if I have the components written in a line like this, whatever, all the way up to, I don't know, maybe the last component's pi. Great number. Highly recommend. However, I'm going to start writing them in a different way. It's not a big deal, just to be aware of. I'm going to start writing them in terms of columns of numbers. So this one that I've written up here would be 1, 2, 3, 4, ... pi. And this is going to become important later when we talk about linear maps and matrices, because there is a distinction between columns written, or vectors written as columns and vectors written as rows. There isn't one in anything we've talked about so far, really, but when we start getting into matrices and linear maps, there will be. So I'm going to start writing them in this way. Not a huge deal. All right, so if I wanted to, I'll isolate this from everything else on the page. If I wanted to compute the dot product of v and w, where v is given by a simple three-dimensional vector -1, 2, -1, and w is given by 2, 4, 6. Why not? Remember that I'm doing this with respect to an orthonormal basis, so these are the components of v. So v is -1 times the vector e1 plus 2 times the vector e2 plus -1 times the vector e3, and so on, where e1, e2, and e3 form an orthonormal basis. then according to our formula for the component form of the dot product, v dot w would be minus 1 times 2 plus 2 times 4 plus minus 1 times 6. So this is going to be minus 2 plus 8 minus 6. And so this is going to be 0. And look at that. So I totally just guessed these numbers, and the dot product has gotten to be 0, which is kind of great for talking about stuff we've already talked about. So what does that mean when the dot product is 0? That means that these two vectors must be orthogonal to each other. So if I were to draw them in three-dimensional space, which I'm not going to do, they would be at a right angle to each other. So an example, I mean, they could be, I've got a three-dimensional space here. We live in one for all apparent purposes. So these two vectors are right angles to each other, but also, if I had a vector that was coming vertically out of the page, that would be at another right angle to the other two. So, cool. Yeah, so let's talk about computing the magnitudes of these vectors. So remember, the magnitude of v is given by the square root of v dot v. Well, v dot v is going to be minus 1 squared plus 2 squared plus minus 1 squared, which is going to be 1 plus 4 plus 1, which is going to be 6. So the magnitude of v is going to be square root of 6. Now, I didn't make this obvious when we started talking about this, but this is in fact the Pythagorean theorem. All right? How is that the Pythagorean theorem? Well, let's go back to the definition of the dot product where, so v dot v is going to be, if I write it in terms of components, arbitrary components, it's going to be v1 squared plus v2 squared plus v3 squared. And so the magnitude of v is going to be square root of v1 squared plus v2 squared plus v3 squared. Now, let's go back to the Pythagorean theorem that we know and love from plane trigonometry. If I have a triangle here, and I have its hypotenuse, I'm drawing them as vectors, and this is E1, this is V1, so this is my vector V1, this is V2, I'm working in 2 dimensions here, this is not a vector. These are the components times E2 and E1. Then the length of the hypotenuse of this triangle is going to be square root of v1 squared plus v2 squared, which is the same, which is saying that c squared equals a squared plus b squared, right? Okay. The next topic that we're going to talk about that's related to the dot product is the distance formula. And so you may have already seen this, but it's probably been a long time since you've seen it. But it comes from essentially the dot product. If I have 2 points somewhere in space, and I want to find the distance between them, and let's say I am here. So this is me, and I'm at the origin. Then finding the distance between this point A and this point B is the same as finding the magnitude of this vector. You can imagine if I were at A and I wanted to go to B, finding the distance between the points is just finding out how long I'd have to walk, right? So what I need to do is find the magnitude of this vector. Well, how do I do that? I don't know this vector right away, but I can figure it out because I can find the vector to B and the vector to A, and I will call this vector here D for distance. And this is my B vector and this is my A vector. So then from the rules of linear algebra, you can see that D is going to be the vector B minus the vector A. Okay? So if I want to compute the distance between these points. Now I need to compute the magnitude of D, which is going to be the magnitude of B minus A. Now, what is B minus A? Well, remember that in terms of components, B is given by B1 E1 plus B2 E2 plus all the way up to Bn En. So this is a two-dimensional example, but in this math over here, I'm working in n dimensions, arbitrary dimensions. I wanted to do this to make sure that you guys get an intuition for working with higher dimensional spaces that you can't visualize, but the math works out the same in instances that you can visualize. You just have more terms, essentially. So higher dimensions are nothing to be afraid of. And then this is going to be minus the component representation of A, which is going to be A1 E1 plus all the way up to An En. Now, because of the scalar multiplication and distributivity properties and associativity properties of linear algebra that we talked about in the first lecture with the axioms, this is going to simplify to this expression, B1 minus A1 times E1 plus all the way up to Bn minus An En. So the components of the difference, the components of the vector that represents the difference of the two vectors, is just the difference of the components. Okay? So that means that if D is given by B1 minus A1 times E1 all the way up to Bn minus An En, then the magnitude of D squared is going to be D dot D, which we know from the definition of the dot product, and that formula we derived is going to be B1 minus A1 squared plus B2 minus A2 squared plus dot 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 Bn minus An squared. Okay? Now, this is the distance formula, and then obviously the magnitude itself is going to be the square root of all that. I'm not going to write it all again, but you get the idea. Now, this is the Euclidean distance function, and this comes up all the time in machine learning and computational neuroscience, especially because let's say that you have a data set that has, something like let's say you have a data set where this is your, I'm going to call it the data vector. This is something you measure. And then you have a model that gives you another vector. I'm going to call this the model vector. You want to minimize, if you want your model to describe the data well, you want to minimize this distance, right? Because if you minimize this distance, it's going to make the model closer to the data. And so what a lot of machine learning algorithms and other things end up doing is they describe the data and the model through some vector space, so in the language of vectors, and then they use the Euclidean distance function to represent how well the model does in modeling the data. Okay? And they want to minimize this over the model parameters. They want to find the model parameters that gives you a vector that's as close to the data as possible, essentially. There's a lot of tricks to this because you have to do things like regularization and all sorts of things, but we'll get into those in later lectures. But the idea is that you're trying to minimize this distance. That's really all there is to a lot of different algorithms. And the choice of these vectors and formula is basically amounting to the choice of learning algorithm. So that's, and machine learning technique, that's what it all comes down to. You're trying to minimize some distance function. All right, we're going to talk about one more thing, and that is the projection. So this is an important concept that comes up in a lot of modeling work. So one thing that you can keep in mind in doing this, if you want to, something neuroscience related to keep in mind, is the idea of a receptive field, the basic idea of a receptive field, where let's say there is a vector that I'm going to call RF, and this vector represents the neuron's receptive field or whatever. Then let's say there's a stimulus in the environment, and it's like this in some vector space. A lot of models for neurons rely on computing the projection of the data, or stimulus, so I'm going to call this, computing this projection, and what I mean by that is how much is the stimulus like the receptive field. So this new vector here is going to be the projection onto the receptive field of the stimulus. Okay, so that's the picture to keep in mind. Although in general, this doesn't happen in a two-dimensional space, it happens in a large dimensional space. But the math is all the same. So how does this work? All right, where to begin? So as you'll remember, if you remember from trigonometry, if I have vectors like this, and I want to find the projection, what I'm asking for is I want to find this vector. So this is a right angle here. Sorry, that's not drawn well. And you'll remember that we have an angle here, and this is a vector v, and this is a vector w. And basically, if you remember, the length here, the length of this thing here is going to be the length of v, which is the hypotenuse of that right angle triangle, times cosine of theta, right? So you'll start to see here that we have the dot product kind of emerging, because the dot product of v and w is length of w, length of v, times cosine of theta. So to transform this into that, all we got to do is find v dot w divided by the magnitude of w. Okay? Now, this quantity right here is not a vector, it's a number, because the dot product is a number and the magnitude is a number, the norm is a number. We want to find this vector. So how do we do that? Well, we want the length of this vector to be this quantity, which I'll call L, and we want the direction of this vector to be the same direction as W. So at first glance, you might just think, well, we'd do L times W. But this is a problem because the length of this vector, this is now a vector because we have scalar multiplication, the length of this vector is not L because W doesn't necessarily have a unit length. So to get a unit vector, that is a vector that has a length of 1 in the direction of W, what we do is we form the vector W divided by the length of W. Now, what is the length of this vector? So we have a vector divide its magnitude, and we want to do the magnitude of this, then this is going to be, remember, W1 in components divided by the length of W plus W2, that's going to be square root, squared over the length of W. Squared? These are all squared. My apologies. Plus all the way up to Wn squared over the length of W squared. And we can simplify this by pulling out the 1 over length of W squared, and under the square root it's going to give 1 over length of W times 1 squared plus all the way up to wn squared. But this is just the length of w over the length of w, which is 1. So w over the magnitude of w is a unit vector. This process of taking a vector and dividing it by its norm is called normalizing it, appropriately enough. So what we need to do then is we need to take the quantity, if we want to make the projection, we need to take the quantity L, which is our length that we want that to have, which is w dot v over magnitude of w, and multiply it by the unit vector in the direction of w. So this gives us the formula for the projection as w dot v over length of w squared times the vector w. Sorry, this is not an equality. L is given by, I said, this is L. This is now a vector, which I'll call P for projection. And in the picture that we drew, if this was V and this is W, then this vector here is P. So this allows you to kind of find how much of one feature is in a different feature or a different piece of your data set, or how similar they are. Because one thing that you'll notice is that if the length of this projection vector is going to be the maximum when v is equal to w. Okay, let's review a little bit what we've covered in this second lecture. We talked about the concept of an orthonormal basis, where our basis vectors are at right angles to each other, and they all have length 1. To talk about lengths and angles, we introduced the dot product, which is related to the lengths and the angles of the vectors, and it produces a number from two vectors. That kind of represents how similar the vectors are to each other. If they're orthogonal, then v dot w equals 0, and they're basically nothing like each other. They go in completely different directions. There's no part of w that can be explained by v and vice versa. We talked about the utility of using an orthonormal basis and giving us a formula for the dot product that just was the components of the vector multiplied with each other. Sorry, all the way up to however many dimensions you're working in. And then we talked about the norm of a vector computed from the dot product, which is the square root of the dot product with the vector with itself. And then we talked about the distance formula, the Euclidean distance formula, and how it arises from the Euclidean, from the dot product, and how this, we gave a brief overview of how this leads to cost functions in ML, stats, machine learning, stats, comp neuro, all sorts of things. And then we talked about projections and how to compute them from the dot product, and what they mean in some computational neuroscience applications and how they mesh with the idea of a receptive field. So that's all for now. Please let me know if you have any questions about any of the topics we discussed. I'll be more than happy to answer them. And feel free to explore any one of these topics and find other resources online if there was anything that wasn't clear. So, all right, I will see you next time for the second week of calculus, or sorry, second week of linear algebra.